So let's continue the discussion on RAID. So if you remember the previous lecture, RAID 2 use Hamming code, error correction code, and they use bit by bit. They distribute this 4-bit to each disk.
Just before, is it possible to do RAID levels with RAM modules to increase the performance? Because I was thinking about it and there's no reason why you shouldn't, but I don't know if there's something else for it.
Actually, for the memory, the maximum bandwidth, memory to CPU bandwidth is limited by bus bandwidth.
Right.
And data bus usually is only 64 bits, and they are utilizing 64 bits in parallel.
Okay, so that wouldn't be practical.
So it's something similar to RAID, because if you think about the memory card, it usually has memory chip, 16 memory chips, and front side and back side, and each DRAM chip provides 4 bits each. So 16 times 4 is 64 bits. So they somehow
have it implemented basically.
Yeah, somehow similar. Okay, so if you have 4-bit enabled, you need extra 3 bits, and if you need 8 bit, then maybe we need to add more bits to correct error correction code. And also we can add parity, and regardless of the data size, you just need a single bit to implement this parity. And you can actually put this parity at the one disk, or you can also interleave. Oh, okay, this is different. Okay, so either ECC, Hamming code, or parity, but this is bit interleaved parity. In this case, from RAID level 4, 5, 6, it's a little different. So RAID level 4 to 6 make use of an independent access technique, which means each disk can operate independently. So before, to transfer, all disks works in parallel, because they bit by bit they are distributed, right? So here, block level distributed. So whenever there is a transfer from here to there, and so on. So each member disk operate independently. So you put a single block here, second block here, third block here, fourth block here, and this block, so this disk can provide a block. So it's not bit by bit, it's block by block. And if you have requests going to different disks, then it can also operate in parallel, but each disk are operating independently. It's not bit by bit, it's block by block. Do you know what I mean? Okay, so before it's like bit 0, bit 1, bit 2, bit 3 in each disk. Okay? So to transfer, they should locate the track and they should work in parallel. It's like they should be synchronized, right? Because 4 bits are distributed across 4 disks. But in this RAID 4 to RAID 6, it's like B0, B1, B2, and a single block is stored here. Maybe next block is stored here. And each block can be transferred to the system independently. Okay? So this is block maybe 0, block 1, block 2, and block 3. Okay? So each disk can operate independently. They don't have to be synchronized, because they can transfer entire block. Okay, and if there are multiple requests from the system, and if the requests go to different disks, then maybe 4 disks can work in parallel also. Okay, but if all the requests are going to this first disk, then there are some conflict. So if you remember computer architecture class, it's like more interleaved memory organization. Okay, and the parity you can calculate bit 0 here from the first block, bit 0 here from the second block, bit 0 here from the third block, and so on, and then you compute the parity and store there. Okay, it's something like block interleaving, and it's called block interleaved parity. Okay, so it's suitable for application with higher request rate, because if you're requesting many different blocks, then if they are distributed across this disk, then they can all these disks work in parallel. Okay, but not suitable for application with high data transfer rate, because if you do bit interleaving, always they work in parallel and all the disks should work simultaneously. But here it depends on the request. So data transfer rate might be low, but if your requests are going to different blocks, and then this might give you more performance. Okay. And if you organize in this way, then a write to disk X1 is here, so this is disk X0, X1, X2, X3, required 2 reads of disk X1 and X4, and 2 writes of disk X1 and X4 to compute. So whenever you modify the block on disk, the second disk, you also need to modify the parity. Okay, so sometimes intuitively to compute the parity you have to read all these other disks as well, right? But you can avoid reading these other disks. But if you do this kind of computation, okay. So to compute the in general, this is the fourth disk. Okay, fifth disk. So X0, X1, X2, X3, X4. Okay, so X4, this parity should be exclusive OR of the other bits distributed in each disk. Okay, and the X4-I is the new parity, should be calculated using these are not changed, but you update only disk X1. Right, this is a new data, right? So you have to compute this one. But if you remember this digital logic, then you can add X1 of I exclusive or X1 of I, because these are the same, right? Okay, so far it's easy, right? No?
That on the second line, right?
So these actually exclusive or these should be the same, so this should be 0. Right?
Oh yeah, we can take two.
Yeah, 2 exclusive or if they are complement, then that's here, that's 1. So if it's same, then this should be 0. But X exclusive or 0 is same as X in exclusive or computation, right? If it's I am 1, if it's 0, then it should be 1.
Yes.
If I am 1 and it's 1, if I am 0 and this is 0, then it should be 0, right? So it's same as me, right? Okay. So you do this, you add this x1 of I and x1 of I, and then you move this x1 of I here and move x1 dash of I here. Okay? It should be the same. And if you look at this computation, this should be same as x4 of I, right? Because these are the parity calculation for x4 of I, and remaining should be the same. So that means to compute the new parity after the write, you should read the old value of parity, old value of x1 of I, and the new value of x1 of I, then you compute exclusive OR, then you can compute this new parity. Okay? So you don't have to read x2 or x3. Okay? So this means you have to read 2 two old value, right? And you have to write this one, and you have to write this one. So you need two read and two write. Okay, that's what it means. Therefore, to calculate the new parity, you must read the older user data, which is x1 of y, and the old user parity, which is x4 of y. And then you have to write this one, and you have to write that. So every write operation must involve the parity disk, and sometimes this should be a barrel line. Okay? So this is disk level 4. Okay? Level 5 is exactly same, but you distribute this parity across the disk. Then you can allocate as a round robin scheme. If you distribute this way, then the loss of any one single disk does not result in data loss. So this is more reliable. So it is widely used. Okay, it's same as before, but you distribute this parity across the disk. And level 6, you actually have one parity and you compute the other parity. This is like another. You can use this for exclusive OR, and the other parity you can use maybe independent algorithm to check the parity. Maybe you can use even parity or something like that. And then it can provide more reliability. But this actually incurs more write penalty because each write affects two parity blocks. Right? You have to write this one and you have to write this one. And usually from the performance simulation, RAID 6 can provide more reliability, but it actually decreases the write performance about 30 times. So this is not open use. Whenever if you need much more reliability, then maybe you can consider this option. Okay? This is RAID level 6. Okay. Okay. Disk cache is a buffer in main memory for disk sectors. So in main memory, you can have some disk blocks. So disk sectors. So this cache contains a copy of some sectors on the disk. Okay. So whenever an I/O request is made for a particular sector, a check is made to determine if the sector is already in the data cache. Okay. Then the request can be satisfied from the disk cache. Otherwise, the request sector is brought in from the disk and is put into the disk cache. So the next time when you access, then you can read from the disk cache. You don't have to go to disk drive. So it's often used to improve disk access performance. And because it's a cache, you need a replacement algorithm. You can use a list recently used, same as the cache in the computer system. The block that has not been referenced for the longest time is replaced. It's same as before. It's basically stack. Okay, so you maintain a stack of pointers. Most recently referenced block is on top of the stack. Whenever a block is referenced or is brought in from the cache, it's placed on the top of the stack. Okay, so that's the most recent one. Least frequently used is they replace the block that has experienced the fewest reference count. So they count how many times are referenced from the disk cache. If some sector or some block has not been referenced, for the fewest count, then it is selected instead of RLU. So for each block, you associate the counter, and whenever you access, you increment the counter. So whenever you need a replacement, you find the block with the smallest count and you replace the block. Okay, and this can be problematic because sometimes certain blocks are referenced relatively infrequently overall. It's not referenced, but when they are referenced, there are short intervals of repeated reference due to locality. So you have reference to some sectors very frequently and then not much reference. In that case, it can build up high reference count. After such interval is over, the reference count can be misleading. So even though you have to select this block, you think this block has been referenced very frequently because for the past time, it has been referenced very intensively. So that's one of the problems. Okay, and this is the last homework. Okay, we don't have homework folder, final chapter, file system. Okay, so due by next Tuesday, and our final exam is next Thursday, right? Okay.
Do we have homework next week? Do you have a class next week?
No, we don't have class next week. I'm trying to finish by today.
But how can
If I can, but if I cannot, then maybe we have to extend to.
but how can I submit homework?
You can submit to the TA, which is room 236 in this building. Okay? Okay, finally the final chapter. Let's try to complete this by today. We have about 50 minutes. This is the final subject, file management. In most applications, files are quite important. It's key element. So except some real-time systems, files are used as input and output. So if you do some application, usually files are input and also output. So virtually all the operating system provides file system. File has some desirable properties. It has long-term existence because files are stored on secondary storage, which are non-volatile storage. So if you want to keep them, then you have to store as files, right? Otherwise, memory or cache, these are all volatile memory. And files can be shared between processes. And file has names, and it also has some access permissions that permit controlled sharing. Okay? And file also can have some structure tailored for particular application. We'll study what kind of file structure is commonly used. So it can be sequential file or index file and so on. And files can be also organized into hierarchical structure. So we have a directory, right? And can reflect relationship among the files. Okay. So file system provides some means to store data. So whenever you store data, you organize as files. And it also provides some functions that can be performed on files. So file system, the typical operations are you can create a file, delete a file, open a file, or close a file, read or write, and so on. And with each file, you maintain a set of attributes. Okay, so who is the owner of this file, and what is the creation time, the time last modified, and so on. And file structure, from small to large, you can view the smallest structure is a field, or a collection of field can form a record, and a set of records can be a file, and then you can maintain file system, or you can also have database system, which is somewhat different from operating system. So if you maintain a database, then usually it's maintained by database management system, which is independent of the operating system. So we'll focus on this structures in the file system. Field is a basic element of data. It contains a single value. So it can be maybe student name, date of hire, or something like that. And each field can be fixed length or variable length. Record is a collection of related fields, and it's treated as a unit by an application. So maybe you can have an employee record or student record which has name, social security number, this is some identification number, and the job, date of hire, and so on. The record can be also fixed or variable length. And also a collection of similar records is a file. So field and a set of fields is a record, a set of records is a file. Okay? And its file is treated as a single entity by user and applications. It can be referenced by a name. It also has access control restrictions, and these access control restrictions usually apply at the file level. The file has some access permission, whether it's readable or writable or executable, and so on. Database is a collection of related data. It may contain all the information related to an organization, maybe company database or something like that. It consists of one or more files, relationship among the elements of the data are more explicit, and it can be shared by a number of different applications. Okay. File system objective. These are just general remarks on the file system. So what is file system? File system is a set of system software that provides service to users and application so that they can use these files more conveniently and safely or reliably. And typically the only way that a user or application may access file is through the file system. You cannot access file individually by yourself. You have to ask the file system, which is part of operating system. Okay? And the objective of file system, they should meet the data management needs of the user. They should guarantee the data in the file should be valid. And file system also deal with performance optimization to increase throughput or to increase response time depending on the application. This is more system level performance. This is more time sharing environment, user level performance. Okay? And provide I/O support for various storage device type, either CD-ROM or disk drive or flash. You can support same file system with same interface. It should minimize lost or destroyed data, so it should be more provide some reliability. And it provides a standardized set of I/O interface routines to user process. In case of multi-user system, they provide I/O support for multiple users. Okay, you can just read through the requirements of the file system. Each user should be able to create, delete, read, or write, or modify files. May have controlled access to other users' files. So they should be able to share, but they should be controlled by access permission. May control what type of access are allowed to each file. And sometimes you should be able to restructure the file tailored for each application or each problem. You should be able to move data between the files. You should be able to back up and recover files in case of damage. And you should be able to access files by name rather than by numeric identifier. Okay, so to provide abstraction to the user, and you should do this operation. This is what we are doing at the computer system. So in general, file system architecture can be viewed like this. So this is users or application. These are the device, storage device. These are more high level, these are more low level. At the lowest level, you have device drivers, and then basic file system, basic I/O, supervisor, logical I/O, and these are the different file structure. So this is more like file system. This is close to operating system concerned. This is to the user. This is more like file system. Let's look at each one. Device drivers. It's operating at the lowest level. It communicates directly with peripheral device. It's responsible for start and end of I operation on the device. It's considered as part of the operating system. So you can view this as if you divide. Even though file system is also part of operating system, if you divide file system from other operating system, these are operating system, these are the file system. Okay, file system is more user level. It deals with files and record. These are more operating system level. They deal with disk device or scheduling or blocks, disk blocks. Okay. Basic file system is also referred as physical I/O. So you have logical I/O, this is physical I/O. Physical I/O. It's primarily interface with environment outside the computer system. It deals with data blocks, okay, because low level, they deal with blocks. File system, they deal with records. Okay, they deal with block placement on the secondary storage and main memory buffering. It's also considered as part of the operating system. The basic I/O supervisor is also part of the operating system. It's responsible for file I/O initiation and termination. It maintain control structures that deal with device I/O, scheduling, and file status, and also disk scheduling to optimize performance, assign I/O buffers, and allocate secondary memory. From logical I/O, this is part of the file system. While basic file system, this is belongs to the operating system. It deals with blocks. Logical I/O deals with file records. So either records are related to file system, lower level, page file system is physical I/O. It deals with disk blocks. Okay. Logical I/O provides general purpose record I/O capability and maintain basic data about files. Okay. And access method is the level closest to user. Different access methods reflect different file structures and different ways of accessing and processing the data. It provides standard interface between the application and the file system. It's file structure. Okay, so you can read the textbook also. So you can view this as top-down or sideways. These are the file system. These are the more operating system. Records are in between. So user or application performs some file operations such as create, delete, read, or write, and then you first locate this file through the directory management. Okay, so you locate the file, and then you have to do some access control. So to purpose it, only the authorized users are allowed to access particular files in particular way, whether read or write or execute. Okay. So in general, this level they translate user command to file manipulation command. Okay. And here file manipulation commands, it depends on the access method, which are the structures. So we study different structures of file system, and then it's translated to records, and then records are translated to blocks. So you do some blocking, and you do some buffering, and you, through the file allocation, you allocate free blocks to file. You also do disk scheduling to optimize performance, and you have to maintain free storage to allocate files and so on. So we'll discuss some of these issues in the following slides. Okay, so these are related with file system, these are related with operating system, and these are overlap. Okay, file organization is the logical structure of records. So a set of fields become a record, a set of records become a file. Okay, and there are different file organization. File means there is no organization. You just put the records as it arrives. Okay, that's the file. Or sequential file. You can have index file, index sequential file, or you can have hashed file, and so you look at each file organization, and in choosing different file organization, you should consider several criteria. These are the important criteria. It should provide short access time. File access should be short, and it should be easy to update. You should minimize storage waste. It should be simple to maintain. It should be reliable, right? But sometimes these criteria conflict between each other, so there are some trade-off. And which criteria is more important depends on the application. Okay, so if a file is used only in batch mode, then rapid access of single record is not important. You just focus on the throughput because it's batch, right? Time sharing is different. For a file on a CD-ROM, this is read-only file, so you don't have to consider ease of update and so on. So it depends on application. Okay, let's look at these file organizations. The first one is file. File means the least complicated form of file organization, which means there is no file structure. Okay, data are collected in the order in which they arrive. They just file them. Okay. The purpose is simply to accumulate the mass of data and save it. Records may have different fields and similar fields in different order, so there is no structure. So you have to, if you want to find some particular record, you have to search everything. So the performance will be very slow, but it's easy to maintain because there is no structure. Each record is a variable length, as you see, and variable set of fields, but they are accumulated in chronological order, in time order. Okay, this is file. The most simplest one, the second simplest one, but the most common form of file structure is a sequential file. So all the records have the same length, it's fixed length record, and same number of fixed size fields. Okay, and you have a key field which identify the record uniquely, and the records are stored sequentially based on the key field. So you, based on the key field, such as maybe student ID, you can sequentialize all the records, and all the records have the same field and same length. Okay, sequential file. It's good for batch application, right? Because you store them sequentially in the key order, but it's bad for interactive application. Random access is slow because you have to search sequentially. And addition to a file is also slow because whenever you add, you have to move. Or whenever you delete, you also need to move. So this is sequential file. Indexed sequential file adds an index to the file to support random access and adds an overflow file. It can greatly reduce the time required to access a single record. Okay. So if you have a sequential file with 1 million records and 1,000 entry index, if you have, and to search if you want to access a particular record, you have to search the index first. And there are 1,000 index, so if you search sequentially, on average you require 500 access to the index file. Okay? And then from the index you find some region that you need to search, right? So the entire record, 1 million records is divided into 1,000, which means there are 1,000 maybe blocks. Okay? So in the block you need to find a specific record which require 500 access. So total you require 1,000 access compared to 500,000 access in a sequential file. So access time can be improved substantially by adding an index file. You can also have multiple levels of indexing to provide greater efficiency. So this index can be made hierarchical. And the sequential file, whenever you add or delete, you can put overflow file to add. So there are pointers, and you don't have to move this main file for addition. So you can improve the addition speed as well. Okay, this is indexed sequential file. Indexed file, problems of the indexed sequential file is it's efficient, but it's limited to a key field because it's basically sequential file. You add index file. Right? If you want to search this file with different field, then you have to organize file as an index file, which means for each field you have an index. Okay, index. So for the index file, you have multiple index for each field, and records are accessed only through index. And the index can be exhaustive index, which means it contains an entry for every record. It can be a partial index. It contains an entry to record where the field of interest exists. Okay? If you don't exist, you just ignore. Okay? And since you have a index, you can have variable length records. It's used mostly in application where timeline of information is critical. And so if you need fast access, you have to implement this way. This means airline reservation system, inventory control, some real-time system. Through this index file, you can improve access performance. Okay? This is index file. Hash file, you use hashing, access directly any block of a known address. Make use of hashing on the key value. So to access a single record, you just need a single access. Okay? So you can provide very fast, very rapid access. Fixed length records are used. But the assumption is it's used when records are already accessed one at a time. If you access multiple records, then you have to hashing multiple times, then it might be slow. But if you access one record at a time, hashing might be provide best performance. So the example applications are directories, maybe telephone directories, maybe pricing tables or schedules. You can have, if you want to search record by record basis, then this is the most efficient form of file structure. Because hashing means if you don't have collision, it requires only a single access or a single record access. But for multiple record access, it should be slow. Okay, that's the hash file. Okay, let's go to directories. I think you know what is directory. Directory contains information about the files, including attributes, location, and ownership. And directory itself is maintained as a file in the file system. These are the directory information. So from the Windows or Linux, you already have seen this kind of information. So usually if you do directory list, then you can find the file name, right? File type, whether this is text file, binary file, or binary module. So maybe .exe file or .txt file or maybe DOC file and so on, file type. And file organization, whether it's index file, sequential file, or hashed file. And address information, the volume where this file is stored, disk volume. So we'll discuss what is volume at the end of this lecture. Starting address on the secondary storage, so cylinder, track, and block number, and the current size and the maximum size. This kind of information. And access control information, who is the owner, and access information. Sometimes for each file you can provide username and password so that only authorized user can access the files, and access permissions such as whether readable, writable, executable. Okay, and usage information, they created, who is the creator, time last read, and identity of the last reader, day last modified, and identity of modifier, date of last backup, and current usage. Current usage means information about current activity on the file, such as process or process that open this file, whether it's locked by a process, whether the file has been updated in main memory, and so on. Okay, these are the directory information. Okay, this date can be time, right? So these are just conventional directory information. So what are the directory information you can perform? You can search the directory to find some file. You can create or delete, adding or deleting an entry to the directory. So if you create or delete the file, then you should modify, you should add or delete an entry to the directory. Okay? You can list directory or you can update directory. So if you change some file attribute, they require change in the directory and so on. Okay? For directory structure, in the simplest case, you can have two-level scheme. In general, you can have a three-structured directory. So two-level scheme, you have master directory, which is a single directory, master directory, and below you have user directory. So in the master directory, you have an entry for each user directory. It provides address and access control information. User directory for each user. You can read through. Three-structured directory is something like this. Master directory, but two-level is like this. Only you have master directory and user level directory and files. Okay, that's two-level. Three-structured means you can have subdirectory, below you have subdirectory, and so on. Okay, these are the more general directory structure, and these are the examples. So you have master directory, has three users. If you look at user B, it has two directory, directory world and directory draw. Directory world has another subdirectory, and each directory you have files. Okay. Okay, let's talk about file sharing. For the file sharing, two issues are access rights, what kind of rights, and management of simultaneous access. So you should provide some mutual exclusion and deadlock synchronization and so on. Access rights, you can have this kind of access right. None means may not even know the existence of file, cannot read the directory. Okay? Knowledge, you know file exists, and you know who the owner is, but you must ask the owner to access this file. Execute, you can execute the program, but cannot copy. Read, you can read the file, which means you can copy and you can execute. So all this access right below actually subsume or include these access rights. So it's the relationship is none belongs to here, and this is a superset. Append, you can add data to the file, but you cannot modify or you cannot delete the file. You cannot delete. Update, you can modify or delete or add to the file's data. But, okay, you can maybe add a record or delete a record, or you can modify a record, but you cannot remove the file. It's different. Okay, change protection, you can change the access right. The strongest one is you can delete the entire file. Okay, so it constitutes a hierarchy with each right implying those preceding it. So this assumes all these permissions. This assumes all these permissions and so on. Okay, and access can be provided to different users. Usually the owner, which means usually the person who initially created the file has all the access rights. And the owner can provide access permission to specific user or the groups or the older users. Okay, so specific user means the individual user designated by user ID, and each user has a group, right? A collection of users belongs to a group. You can provide access to a group or to all the users. Okay. Record blocking. So records are logical unit of access for a structured file. So file system deals with records, while blocks are the unit of I/O. So I/O, the below operating system deals with the disk blocks. So to perform I/O, records must be organized as blocks. So you put records into the blocks. Okay, and okay, he's not sleeping. So there are several issues to consider. Should blocks should be fixed or variable size? In most systems, blocks are fixed size because they can simplify input and output. What should be the relative size of block compared to record size? The larger the block, you can speed up I/O. Okay, because disk is more suitable for sequential processing since you study disk I/O. But it may include unnecessary record. If you use a larger block, it has some internal fragmentation like paging that you have studied. So there are three blocking methods can be used. Fixed length blocking and variable length spanned blocking, variable length unspanned blocking. Fixed length blocking, fixed length records are used, and integral number of records are stored in a block. So for each block, you always store a fixed number of records. Okay, and each records are fixed length. So this is fixed block. So for each block, you have two records. These are intersector gap, which we studied when we study disk. So we need put some hardware gap between the sector, and this is raised to the block size because block size is fixed and record size it depends on the file. So there are some leftovers. Okay, internal fragmentation. Okay, and this raised is due to the track. You have to feed in the track. Okay, these are fixed blocking. So all these blocks we have fixed number of records, and the record size is also fixed. Variable length spanned blocking, you allow variable length records, and you can pack into blocks and a block can span two different blocks. The example is like this. So here you put each record is variable size. The R4 is spanned over two blocks. But you need it's bounded by a trap. Okay? And it's also R9 is spanned over two blocks. And it's variable block but spanned. Okay? Variable block unspanned means you don't allow a single record to be spanned over multiple blocks. Okay? So there are some more fragmentation, but it's unspanned. Okay? So you can have this three different blocking. Okay, that's the record blocking. So after using this record blocking, you translate record from the file system to the blocks in the I/O. Okay? File allocation. So a file consists of a collection of blocks. So file is a collection of records, but after translation, file becomes a collection of blocks. The operating system is responsible for the file allocation. So OS allocates free space on secondary storage to files. So it should allocate some free space, free blocks to files. And to do that, OS needs to keep track of free space. They have to maintain free blocks. Okay? File allocation issues. When a new file is created, should we allocate maximum space for the file add-ons or not? Okay? So OS usually assigns a contiguous set of free blocks, and it's called a portion. Okay? So each block you have a record, and a contiguous set of free block is called portion. This is the allocation unit for the file allocation, and a set of portion becomes a file. Okay? So file, portion, block, and record. Okay? OS assigns a contiguous set of free blocks called a portion to a file. What size should we use for the portion? It can range from a single block to the entire file. Okay? There are some range. And what kind of data structure is to keep track of the portion assigned to a file? The example is on a DOS or window, you use file allocation table. So you need to maintain these portions, how these portions allocate to the block. Let's look at the example. Pre-allocation versus dynamic allocation. Pre-allocation, so at the time of file creation, you require the maximum file size to be declared. So for some applications, it's possible to estimate the maximum size. These applications include program compilation, file transfer over the internet, you know the file size. So you can do pre-allocation. But for many applications, it's impossible to estimate the maximum size. In that case, if you do pre-allocation, user or application tend to overestimate the size, which results in storage waste. Okay? So to avoid waste, you allocate dynamically, which means you allocate space on demand. Portion size. So portion size ranges from a single block to the entire file. You have to consider the following. Contiguity of space increases performance. So if you allocate portion is a contiguous set of blocks. If you can allocate large portion, then it should improve I/O performance because it's contiguous. It can be done as a single access, disk access. So it increases I/O performance. A large number of small portions increase the size of table, file allocation table, and need to manage the allocation information. Fixed size portion simplify the reallocation of space. Okay, because this portion is the allocation unit. If it's fixed, then it's easy to allocate, easy to reuse because it's the same size. Variable size or small fixed size portion minimize storage waste. Okay. So fixed size is like paging, and variable size is like segmentation. Okay. So you can have these two alternatives: variable large contiguous portion, or for a portion you allocate on a block by block basis. Variable large contiguous portion, because it's variable large portion, it means you can improve I/O performance. Because single access you can read entire portion, which is a contiguous set of blocks. Because it's variable, you can avoid waste. You can maintain small table because it's large portion. But it's hard to reuse. So you sometimes read maybe some kind of compaction. So this is contiguous file allocation. So single contiguous set of block is allocated to a file at the time of file creation. So for file A, 2, 3, 4 is allocated. For file B, 1, 2, 3, 4, 5. 5 blocks. These are the portions. This is allocated. And they use pre-allocation strategy using variable size portion. Okay. For file C, they allocate these blocks. And file D is 3. File D is this one. File E is this one. Okay. So it can improve I/O performance for sequential processing because it's contiguous large portion. Disadvantage. So you don't have internal fragmentation because it's contiguous blocks, variable size, but you have external fragmentation. Okay, whenever you deallocate. So what do you need?
In case that the file needs to be updated, what do you do in that case? If the file needs to update and the size would be larger than the...
So if they use pre-allocation, so maybe they allocate more space, I guess.
Even if the contiguous
So-
blocks are occupied?
So they first allocate some variable size portion, but if the maximum size is bigger, then they allocate, they pre-allocate enough space so that they can expand, I guess. Okay. So disadvantage after they reuse, if they do not grow, then they have this hold, right? So what do you need? You need compaction, right? To eliminate external fragmentation. That's this variable large contiguous portion. The other is blocks. You can also have chained allocation. Chained allocation means allocation is on a individual block basis. Okay, so this one, blocks, it provides great flexibility. It doesn't have to be contiguous. It's easy to reuse space because these blocks are fixed size. You can allocate to any, but you require large tables. You can have chained allocation, which is you allocate individual block. Each block contains a pointer to the next block. Okay, so this you allocate file B. The start block is block 1, and it has a pointer to the next block. It has a pointer to the next block, and so on. So the total length is 5. File allocation table entry only requires a single entry, and there is no external fragmentation. But it's not good when you need to bring in multiple blocks because blocks are scattered, right? Which means if you consider disk access, then it's going back and forth, so it increases disk access time if you read in multiple blocks. So what do you need? If you want to improve performance, you need consolidation, which means you sometimes move this chained block into a contiguous block, and then you can improve I/O performance. So from time to time, you do some consolidation to improve I/O performance. Okay, that's the chained application. Indexed allocation with block portion. It addresses the problem of contiguous and chained allocation, and file allocation table entry for each file points to an index block. So you have index block. So this file allocation table entry points to index block. Index block is 24. This shows it has 3 blocks. This file contains 5 blocks, and the first block is in block 1, second block 8, and so on. Okay. And index block has 1 entry for each portion allocated to the file. Portion is block on a block basis. Okay, this is called indexed allocation with block portion. You can also have indexed allocation with variable length portion. Okay, you can combine variable length with index. So it's same as before. File allocation table points to index block. Index block point has the first portion starts at block 1. It has its length is 3, contiguous variable size portion. Second portion starts at block 28. Its length is 4. The third portion is at block 14 and its length is 1. Okay. This is called index allocation with value length portion. Okay. So you can have very large contiguous portion or block portion. For the block portion, we can have, consider these two, we can have these three options in general. Okay. Free space management. So if you want to allocate free blocks to files, you have to maintain file allocation using file allocation table. You also need to maintain free blocks as well, right? And this is called disk allocation table that has information about the free blocks. So just as allocate space must be managed, you need to manage the unallocate, that means free space as well, right? To perform file allocation, it's necessary to know which blocks are available, which blocks are free, and disk allocation table is required in addition to file allocation table. In the simplest form of disk allocation table, you can have this bit table, bit vector. A bit vector contains 1 bit for each block on the disk. So like this. So this means this is free, second block is free, third block is assigned, free, and so on. So by scanning this bit vector, you can determine which blocks are free. Okay. Okay, it works well with any file allocation methods, but the size of bit table is relatively small because you need a single bit for each block. But it can be still huge. Okay. For example, if you have a 16 gigabit disk with 512 byte blocks, it requires 4 megabyte bit table, which requires 8,000 disk blocks. Okay. So still very big. And for free block, you can have also chained free portions. Chained free portion is the free portions may be chained together by using a pointer and length value in each free portion. Okay, so you can view this free block as a portion if it's contiguous, and you can chain. It's like chained allocation. Okay, for each chain you have pointer to the next portion and the size of each portion, and you can follow this chain. Negligible space over it because there is no need for a disk allocation table because free blocks are chained. It's suitable for all file allocation methods. Disadvantage, it leads to fragmentation. Every time you allocate a block, you need to read the block first to recover the pointer to the new first free block before writing data to that block. Okay, because assume that you usually allocate the first free block, free portion, to the file allocation, and then the first free portion has a pointer to the next free portion. So you have to read and you have to retrieve this pointer to maintain this chain. Right? So that means every time for the allocation, you have to read the block first, chain first. That's the overhead. And the other option is you can treat free space as a file. Free space are files. And you can use an index table as in the index. So for efficiency, index should be on the basis of verified portion rather than blocks. This approach provides efficient support for all the file systems. So this might be a good choice in general. So you use indexing for free blocks. Okay. Volumes. What is volume? A collection of sectors in secondary memory. The OS or application used for the data storage. The sectors in a volume need not be consecutive on a physical storage device. They need only to appear that way, consecutive to the operating system. So in general, volume means, in the simplest case, single disk is one volume. If you use a partition, if disk is partitioned, each partition can be a separate volume, or sometimes partitions on multiple disks can be considered as a single volume. Okay, that's what I mean by it need not be consecutive. Or volume may be the result of assembling and more smaller volumes sometimes. Okay, so that's the disk volume. That's all. Oh, finally.